Welcome to this video on the role of carbon capture, utilization, and storage, or CCUS, in our transition to a net zero future. We will explore the strategic necessity, various pathways, and the thermodynamic realities of carbon engineering. Part 1 of this video examines the carbon ledger, focusing on how we account for and address global emissions. Global emission pathways show we release approximately 40 gigatons of CO2 annually. To limit warming to 1.5 degrees Celsius, we need both radical emissions reductions and the deployment of active physical carbon capture technologies to bridge the gap. Hard-to-abate sectors present unique challenges, including inherent process emissions, the need for extreme high heat loads that current green alternatives cannot yet meet cost-effectively, and the prevalence of young, carbon-locked assets. In heavy industry, steel production and cement kilns illustrate why CCUS is essential. For cement, chemical calcination creates unavoidable emissions, making CCUS the only viable baseline technology for abatement. Hard-to-abate sectors account for roughly 34% of global CO2 equivalent emissions. Because these industries are vital to the global supply chain, direct point-source retrofitting remains the most economically feasible solution for these complex processes. Point-source carbon capture targets concentrated exhaust streams. It offers thermodynamic benefits due to high partial pressures of CO2, allows for simple modular retrofitting, and is ideal for power stations, refineries, and chemical plants. In Part 2, we explore the technology spectrum for carbon management. We distinguish between point source capture and carbon dioxide removal. While PSC is a defensive mechanism to stop emissions at the source, CDR is an offensive tool that pulls existing CO2 from the atmosphere. Carbon dioxide removal faces hurdles, including the challenge of atmospheric dilution, the need for a large physical footprint, and a significant economic disparity compared to traditional point source capture. Direct air capture, or DAC, uses sorbents to bind ambient CO2. While energy-intensive, DAC provides immense geographic flexibility, allowing facilities to be co-located with clean energy sources or sequestration sites. Nature-based solutions include afforestation, BECCS, and ocean alkalinity enhancement. These vary in feasibility and permanence, highlighting the importance of durability frameworks when comparing biological sinks to geological storage. In our third part, we dive into specific decarbonization mechanics. Blue hydrogen production uses CCUS to capture emissions from steam methane reforming. This acts as a bridge, providing the massive volumes of hydrogen needed by heavy industry today while green alternatives continue to scale. Finally, CCUS plays a vital role in grid stabilization by offering carbon-free baseload capacity, maintaining grid inertia, and providing dispatchable backup power during periods of low renewable generation. Next, we examine the physics of sequestration. In situ trapping involves injecting CO2 into reactive geological formations, like basaltic reservoirs. The acidic solution reacts with minerals like magnesium and calcium to trigger rapid carbon mineral growth, permanently locking the CO2 as solid, unalterable stone. Moving to Part 4, we will discuss the policy and target landscape essential for scaling CCUS infrastructure. To meet Paris Agreement goals, the IEA outlines a mandate to scale global carbon capture from 45 megatons per year to over 5.6 gigatons by 2050. This requires a compounding annual growth rate of over 15% for global capture, transport, and storage networks. IPCC climate pathways confirm that a vast majority of 1.5-degree scenarios require significant gigaton-scale carbon capture and removal to balance our remaining carbon budgets. The IEA Net Zero Roadmap includes milestones through 2050, from deploying 2030 capture targets and 2035 industrial clusters to establishing 2040 international CO2 shipping networks, ultimately reaching 5.6 gigatons of capacity by 2050. Costs for CCUS are heavily linked to CO2 concentration. Higher concentrations mean lower energy barriers, making point source capture the most economical entry point for decarbonizing industry. Global regulatory frameworks are driving this progress. This includes the US 45Q tax credit, the European Union's emissions trading system, and cross-border adjustment mechanisms, all designed to ensure transparent carbon accounting and economic viability. Our strategy balances two pillars: point source defense, which retrofits existing emitters to protect the industrial base, and removal offense, which utilizes DAC and mineral enhancement to address historical atmospheric emissions. In summary, we have covered core concepts like PSC versus CDR, analyzed hard-to-abate industries, explored blue hydrogen production, and reviewed the policies driving global CCUS targets. Thank you for your active participation in this masterclass. We hope this module provided a clear perspective on the role of carbon management in the energy transition. For further collaboration, research proposals, or professional training, please feel free to reach out via the provided contact information.